All right, off to number 15 and maybe a few extras. So let's see what we can do. This is really actually very much a calculus problem, but we are not going to do our solution utilizing calculus because we won't be there for a little while to get to the point where we can use what's called a derivative to answer this problem. We're going to actually use it solving it with our graphing calculator. Later on, I'll show you an analytic way to do that using some methods that have been figured out. Okay, so we've got this container, and this is a really critical piece of this problem right here. Very important. It has a square base and vertical sides. Okay, so I personally am a pretty visual person, so my thing is I'm usually going to come in here and sketch a quick picture right here, get a little bit of an idea. Well, that's not a very good looking box, but that'll work. Boom, boom, like, there we go. So I got myself a nice little 3D box. It says it's got a square base. Now, one of the things that they did not tell me in this thing is what size that base is, but they did tell me that it's made from 1,000 square foot of material. So let's see what we can figure out. So let's say that we call this thing X, and we call this thing X, and let's say I called this thing Y, because I'm not 100% certain what any piece actually is. So what I know is if you look at this and you were to peel this out, this is one of those things you would notice that this side right here is XY. Let me go ahead and highlight that. This side here is XY. That's one of the lateral faces. But because it's a square base, then every single one of those sides has an area of XY, and of course there are 4 such faces that surround it. So the area as a function of X and Y has 4 of those XY faces, but it has an additional part down underneath. I guess maybe I'll do this one in green. This guy down here in the base, that thing has an area of X squared. Now, normally we're not really a big fan of the fact that we have those 2 variables, but that's what's going to happen because if we made X bigger, then Y would necessarily have to be smaller in order to maintain this 1,000 square feet limitation to our question. So we really don't need to write it this way because we know that that area function is actually set equal to 1,000 square feet. And just for the sake of ease, I'm not going to write that 1,000, the square feet into that story. But what I'm going to do is I'm going to go ahead and solve this thing for Y because, again, since I'm going to use my graphing calculator to solve it, I need Y by itself. So let's start by moving that X squared to the other side. And then, of course, to get rid of this 4x that's sitting right there, we're going to divide both sides by 4x. And so now I have that Y would be 1,000 minus X squared. I'm going to divide both sides by 4x. So there we go. Now that is our expression. So clearly as X gets bigger or smaller, it's going to change the value of Y. Bigger X's are less Y. Bigger Y's make less X's. Okay, well, that's fine. So now I have a relationship between X and Y, but now what do I do? But see, they actually gave me something else that I haven't looked at yet. See, I've been using this idea of area throughout this problem, but the question does not ask me about area. It actually says, hey, let's go do this thing and let's find the dimension with the greatest volume. So I haven't even considered that. So the volume of this particular container, the volume of any what we call a rectangular prism, which is a shape where the base and the top are the same and it's connected with rectangles, is just the area of the base multiplied by the height of that shape. And so since the area of this base is X squared, and the height is this Y value right here, we're again back in this situation where we've got 3 variables. I don't know X, I don't know Y, I want V to be as big as possible, but I've got a little connection right here that says the volume is X squared times Y, but we already know that Y is this entity right here. Now, we could actually go for it right here, but I would think it might be smart for us to go ahead and utilize the fact that this X divides in very nicely. So we could cancel this and just leave 1x, or 1,000 minus X squared over 4. We could choose to use the distributive property and like multiply that out and make it 1,000x minus x cubed over 4, but I think I'm just going to leave it as it is. So let's see what we got. I'm using one of these nice fancy new calculators for the very first time myself. So let's see what we got. I have x parentheses 1,000 minus x squared divided by, I guess, just 4, right? Now, again, window-wise, this is important because they're going to do this thing. So what do we have? Well, x clearly, if it's the size of the box, can't be anything that is negative. So the bottom value is going to be like 0. I don't really have an idea here what it is, but at 10 times 10 times 10 is 1,000. So I'm kind of thinking probably somewhere around 10 is going to be sufficient. So I'm going to give it 15 for x max, and the y value in this case, unfortunately, does not represent the y value that we have in the picture right here. The y value for my calculator right now is going to be the value of this volume. And volume numbers get really, really quite large. And so what I'm going to do is I'm going to tell it to go from -10. Although your volume can't be negative, it's sometimes helpful to leave that negative so I can see where 0 is. So I'm going to go up there and I'm going to give it some room. I'm going to give it up to 1,000 because I don't totally know. I mean, if the area is 1,000, I'm thinking the volume might be even larger. In fact, I bet you anything that's not going to be enough. Let me go 5,000, but I might regret that. But let's see. And then, of course, if I'm going from a graph from 10 to 5,000, maybe counting by every 100 would be more than enough, or maybe every 200. Okay, so let's see. Did I do okay? Now, let's see what I got. Now, I'm not totally loving what I see there, so let me try that again. Let's make this a little bit bigger. Let's see. Oh, there we go. So it appears that the volume as x grows gets bigger and bigger and bigger until a certain place over here somewhere, and it comes down. And you might notice right away that it almost looks like a parabola, but I think you know better. That's an x cubed, so it's not. It actually is skewed a little bit to the right. And so we're going to go to our friend the calculate button right up here at the top. And I'm going to go to second, and I'm going to ask my calculator to calculate. And specifically what I'm looking for is that maximum value, number 4. And the calculator wants me to move my cursor to the left of the maximum. It's going to move it to the right of the maximum. It's giving it a lower bound and an upper bound that says, hey, that maximum should be between those. So I'm going to search out the biggest number within that. And it says, hey, your maximum value happens at x is 18.257. Now, one thing that's really kind of important in calc is that we actually don't want to ever round until we're all the way done with this problem, because when they did this, they asked for the dimensions. So I found the base dimension, but I haven't found that height dimension yet. So one thing that I'm going to do is I'm going to go ahead and quit out of this thing, second quit. I'm going to take the answer. Now, the last thing that my calculator found was that value for x. So I'm going to store that as alpha A, because now this value is stored with all of its accuracy out to, billion decimal places, or 9 decimal places, like the closest billionth. It's there. And now let's take a look at what y was. Well, over here, we figured out that the height, the y value, was 1,000 minus a squared divided by a. Oh, times 4. And let's put that in parentheses so it knows it's dividing by both the 4 and the a. Oh man, let's move that down so you can see that better. A little glare. There we are. And I got 9.1. Now you might notice something about those values. 9.128. Do you notice how those are in a 2-to-1 ratio? Yeah, that actually happens, and there's a reason in the mathematics for why that is the case in this story. So, the reality is, because I'm just doing this to help us out, I'm not going to do that, but we should probably in this situation write a simple sentence to say, hey, the optimal values are to have a base that is a square that is 18.257 on a side and a height of 9.19. Wait, I wrote that down wrong. 9.128. So basically, half as high as it is wide optimizes that volume. And I didn't mention that before, but if you go back to that situation that we had in here, we found that value of x, right? So there's something else that we could do that's kind of cool. And that is this y value is sitting right here. That is the value of the volume. And I actually would like to know what happens if I plug in this x value that is that optimal value. So let's see. Now, this is something I'm going to have you guys do a ton in here, is I want you to actually use your calculator to plug something in. So under here, there's variables right there. So hit variables. Your calculator has y variables because that's where we stored this equation. So we're going to go there. I stored that equation as y1. Now, again, back in algebra 2, like f of 4 means plug 4 into f. Well, we're just going to do this. We're just going to say y1 of a, because remember, I stored x as a. So that maximum volume, remember, I guessed that it might be up around 1,000, then I just second guessed myself. That volume that was that maximal value turned into be 3,042.903. And that would be cubic feet. And it's not surprising that the volume was a little bit bigger than that value of the area that we were seeking. Okay, so that's question number 15. I think I've exhausted that one. Now, we're going to go on to number 16. Number 16 asks me to find all the points of intersection of these two curves. X squared minus y equals 3 and x minus y equals 1. But we're going to do that algebraically. So we might use our calculator to validate our answer, make sure we did okay, but we're actually going to use just strictly algebraic methods. But you have to keep in mind that this is a parabola and that's a line. So if you think about a parabola and a line, what could happen is they might intersect twice. It's also absolutely 100% possible that they could come like this and maybe they intersect exactly one place, or maybe it goes like this and the line just misses and I have no solution. So those are all legitimate possibilities, and I'm not sure walking into this problem which one we're going to have, but we're going to find out here in a second. So let's see what we got. So my two curves for number 16 are x squared minus y equals 3, and we also have x minus y equals 1. Now again, when you have two equations with two unknowns, a lot of times we like to stack the equation, so maybe we make one of the variables go away. That is 100% a possibility in this question. We could look at this problem through this lens right here. Now I'm going to write this one here, and I'm going to multiply this one by -1 for a reason. I'm going to multiply by -1, which gives me a negative x, a positive y, and a -1, because you'll notice if we stack that and add down, we're going to have x squared minus x on this side, and we're going to have the number 2 on that side, which is pretty cool. So that turned into a nice little quadratic that's going to allow me to go solve for that x value. Now, factoring is going to be a very important tool for us to solve an awful lot of equations this year. So when we look at a problem like this, this is one of the nicest little questions. Hopefully you guys can factor pretty quickly. You know that x squared has to be 2x's. 2 is prime, so it's got to be a 2 and a 1. I'm looking at a negative and a positive to make that true. So it appears that the two values that make this true would be -1 or +2. But keep in mind, I'm looking for points of intersection. So the x value is -1, or possibly the x value is 2. And clearly, if we wanted to come up here, we could say then that x minus 1 is equal to y if I just kind of move these things around a little bit. So if I took this x value and I subtracted 1 from it, I would have -2, and if I take this x value minus 1, I have 1. So it appears that my points of intersection are there. Now, I did mention that you could do something else. So over here on the side, I might say, well, x squared minus y equals 3. Instead of using the elimination method, we could choose to use substitution method. And notice that I isolated this thing out. I took that y out, but I know that y is x minus 1. And that's going to lead us through a couple of little steps right back to this story right here. And so don't believe that we will always get such pretty answers, but in this case, we did. So that's number 16. And I think that's where I want to end this particular video. We'll just have those two because those are pretty big questions. Okay, I'll see you back on the next one.